Welcome back, guys. It's Chapter 2, Part 2 for Chem 104, still doing chemistry and measurements, but in this section we're going to take all the things we learned about equalities, prefixes, conversion factors, put them together to start solving some problems. Make sure that you have a calculator handy, especially for live lecture. We're going to be working a lot of practice problems, so just be ready. First, we're going to use conversion factors to do unit conversions. We're going to change from one unit to another. Before we start throwing around numbers and we start punching stuff into our calculators, problem solving is a skill and you need methodology to be successful. Oftentimes in chemistry, you need to know how to convert from one unit to another because you need to. Let's say you buy a reagent and you have X number of units of activity per microliter, right? It's an enzyme. Well, now you need to figure out how many micrograms of enzyme are in 2 microliters, right? That's a lot of conversions. They're not difficult, but you need some kind of a method for solving these types of problems, because if you end up doing chemistry in the lab, you'll absolutely encounter these types of problems just in setting up experiments. We're not even talking about analyzing data yet. Problem solving in chemistry requires the identification of the given quantity units. You need to determine the units needed, and then you can identify the conversion factors that connect those two quantities. So let's start solving some problems. I will highlight the different steps used to problem solve, and these steps can be used for any problems. You always have to read the question, identify your given information, what you're being asked, and then pull out the pieces of information that you've learned in order to connect what's been given to what you need to answer. Here we go. If a person weighs 164 pounds, what is the body mass in kilograms? And we're given this equality. 1 kilogram is equal to 2.20 pounds. So we're starting off with 164 pounds and the equality 1 kilogram is equal to 2.20 pounds. I like to rewrite the question as well. £164 is equal to question mark kilograms. That's our question, boiled down. We know that if we have an equality, we can write conversion factors. And one of those conversion factors will help us get from pounds to kilograms. The conversion factors look like fractions. I will from now on abbreviate conversion factor CF. So from our equality, we can write 1 kilogram in the numerator, 2.20 pounds in the denominator, and we can write the reciprocal, the 2.20 pounds in the numerator, 1 kilogram in the denominator. Now we need to choose one of these conversion factors that will get us from pounds to kilograms. If we're trying to get rid of pounds, That means to cancel out the pounds, we need pounds on the top in the numerator and pounds on the bottom in the denominator. Right now, we've got pounds in the numerator. We're looking for a conversion factor with pounds in the denominator. That's going to be this one, 1 kilogram over 2.20 pounds. Fill in your conversion factor. Before you pick up your calculator, make sure that the units cancel when you multiply your given information by your conversion factor. This will come very, very, very handy when we're using more than one conversion factor. It's easy to write one the wrong way or think you need it one way and you actually need to flip it. Doing this unit analysis will save you a lot of points. Pounds in the numerator, pounds in the denominator. That's the only way that we can cancel it. When we cancel the units, we're not canceling the numbers. So to do this, we're going to multiply 164 times 1 kilogram, which that's the unit that we want left. Then you're going to divide by 2.20. Your calculator is going to give you a number. But we know that calculator doesn't give us sig figs or units. Now let's go back to our information. We've got 3 sig figs in 164 pounds. We also have an equality that contains a measurement. This is not a definition that is exact. This is a measured number. There are 3 sig figs in 2.20 pounds. So our answer must have 3 sig figs. Our last retained digit will be this 5. We look at the 4 next door and determine if we're going to round up or just drop everything off. 4 is 4 or less, so we're just going to drop everything off. But that answer isn't complete. We need units. We were converting pounds to kilograms, so we should also have kg at the end. That is the complete answer. If you stopped anywhere before there, including just having the correct number with the right number of sig figs, it's incorrect. Make sure that you have those units. Let's do another problem. If you would like, you can pause it here and give it a try. I'd encourage you to do that. Otherwise, you can just watch along, put it in your notebook, and be ready to try it when we have lecture. A rattlesnake is 2.44 meters long. Now, I don't like snakes, okay? This is just an aside. Me and snakes, we don't go together. So when I first moved to North Carolina and I heard about all the snakes that are venomous, poisonous, whichever one it is, I said, oh no, we have made a mistake. But I have not encountered a snake yet. I pray my favor continues. But me and snakes, no. When they said, oh yeah, snakes like to hang out in crawl spaces under houses, I said, wait a minute. We don't do that. So this problem, I'm going to be real. The first time I read this problem, I said, oh wait, a rattlesnake, can we change that to something else, like just an earthworm? But I decided to keep the integrity of the textbook, let it be true to itself, and I will be true to myself. I don't care how big the rattlesnake is. I don't want to see it. I don't want it to exist on my property or in my world. Anyway, that was an aside. You're welcome. A rattlesnake is 2.44 meters long. How many centimeters long is the snake? I like to rewrite the question. And I also write all the given information. So our question is, we've got 2.44 meters. How many centimeters is that? What we're given, obviously 2.44 meters, but we also know the relationship between meters and centimeters. The charts that I was talking about that we went over with all the prefixes from the first part of this chapter, you will need them here. One meter is equal to 100 centimeters. Now I just know that just from doing this for a long time. If you were looking at the chart, or if you just say, okay, I have centimeter, I have 1 centimeter, what is that equal to in meters? And then you look at the centi, what does that mean? Centi means 10 to the minus 2. So both of these equalities say the same thing. They describe the same relationship. It's just different numbers describing it. So we can say 1 meter is equal to 100 centimeters, or we can say 1 centimeter is 10 to the minus 2 meters. I will show you both ways, and we'll still get the same exact answer. Now that we've got our equality, we can write conversion factors, which I abbreviate CF. You just write two fractions. 1 meter over 100 centimeters, and we can also have 100 centimeters over 1 meter. We're trying to go from meters to centimeters. We've got meters in the numerator. To cancel it out, we need meters in the denominator. You choose the conversion factor with meters in the denominator. Then before you touch your calculator, I know it's tempting, don't. Make sure your units cancel and you're left with the unit you want. We're good, so we can go through and do our calculation. You're doing 2.44 times 100 divided by 1. You should get 244 centimeters. Now let's think about sig figs. There are 3 sig figs in our measurement. Our equality is a definition, so these are exact numbers. The meter and the 100 centimeters, same unit system. We're talking about the metric system. It's a definition that's exact. We don't worry about those numbers when it comes to sig figs. So our answer should have 3 sig figs. And it does. Done. Now let's say that you wrote the other equality. 1 centimeter is equal to 10 to the minus 2 meters. We still have to write 2 conversion factors. There's 1. You flip over to make the second. And then we set up our problem. Still looking for the conversion factor with meters in the bottom. Write it in. And when you do this math, you should still get the same thing. 10 to the minus 2 is the same thing as 0.01. These two equations look different, but you get the same answer. The equalities are the same. I won't solve every problem with both equalities like this when it deals with a metric system conversion, but just know there are two ways to do this. Whichever one makes most sense to you, that's the way that you go with. So we can't just stop there. We're in college. We've got to make it a little bit more difficult. We're going to start solving problems that need 2 or more conversion factors. And in these problems, you set up one conversion factor after the other, and you have to arrange them in a way that will cancel out the units, and you still end up with what you need at the end. Let's do an example. I always think examples are better than just saying it in words or reading it. A doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. If tablets contain 75 micrograms of Synthroid, how many tablets are required to provide the prescribed medication? So our question how many tablets? Right? That's what it boils down to. So our answer should be the number of tablets we need to give this dosage. What are we given? The dose required is 0.150 milligrams. We also know that a tablet contains 75 micrograms. Those words describe an equality. One tablet equals 75 micrograms. We also know something else. We can write an equality that will equate milligrams and micrograms. Let's think about it. If I have 1 gram, that means I have 1,000 milligrams. And again, this is from the chart. You can see that both of these measurements have gram, so we're going to use the gram as our kind of central unit. And we're going to write 2 equalities, one with milligrams and one with micrograms. Then we can smush them together. We also know that 1 gram is equal to 10 to the 6th micrograms. This is the same thing as 10 to the 3rd. Make sure I give you scientific notation too. With these two, we can put them together and say 10 to the 3rd milligrams is equal to 10 to the 6th micrograms. And if you want to simplify that further, you can. I'm going to leave it here because we don't have to go further. You'll still get the same answer. So that's our second equality that we'll need to solve this problem. So here's what we do. We've got to set up an equation that takes us from our dosage in milligrams to the number of micrograms and then the number of tablets. So let's start. We've got 0.150 billigrams that we need to have. We're going to write in our first equality to go from our dose in milligrams to our dose in micrograms. That means we're going to start here. To cancel out milligrams, we need to put milligrams in the denominator because they're already in the numerator. The number associated with that in our equality is 10 to the third. That leaves 10 to the sixth micrograms to go in the top. For our second conversion factor, we need to take the number of micrograms and get to the number of tablets. Micrograms are in the numerator, so micrograms must go in the denominator. The number associated with that is 75 in our equality, and that is for 1 tablet. Make sure to check your units. We're converting from milligrams to micrograms. Check. And from micrograms to tablets. Check. Now you can put all of this mess into your calculator. 0.15 multiplied by 10 to the 6th divided by 10 to the 3rd multiplied by 1 divided by 75. Your calculator will tell you too. However, we need to think about sig figs. In the equality where we're taking milligrams and micrograms, that's a definition. We don't need to worry about numbers there because those are exact numbers. Sig figs don't count. However, with the tablet, we've got this 75 micrograms. And that has 2 sig figs. And of course, the dose required has 3 sig figs. If that's what our calculator displays, we need to represent 2 with 2 significant figures. Add a significant 0. So that is a concept from, again, the first part of chapter 2. So if that still feels kind of fuzzy, maybe you need to rewatch it, or just come to lecture and you'll hopefully get what you need. Like I said, we're doing a lot of problems this time. So I hope you have your calculator. If you didn't get it, remember this is a video that you can pause. Go get it. All right. How many minutes are in 1.4 days? The question is simple enough that I'm not going to rewrite it. We are given an amount of time, which is 1.4 days. But we also know something about time because we've kind of been around for a while. 1 day is equal to 24 hours. That's our first equality. We know something about hours too. 1 hour is the same thing as 60 minutes. We can use these two equalities to go from days to minutes. We'll write out our conversion factors. I didn't do that 100% the last time. I wanted to show you how you can kind of fill in the conversion factors as you go. But I'll kind of alternate between the two just so you can see both. So here are our conversion factors for equality 1. 1 day over 24 hours. And then you flip it around. 24 hours over 1 day. For the second equality, you've got 1 hour over 60 minutes. And the reciprocal, 60 minutes over 1 hour. Starting with 1.4 days, our given information, we need to choose the correct conversion factors to cancel out days and get to minutes. First, we go to hours. Let's write our plan above because I think that's helpful too. We're going from days to hours, and from hours to minutes. That way, when we do our unit analysis, we can check it off and make sure that we're on the right track. Days are in the numerator. That means days must be in the denominator for our first conversion factor. Now that we've got hours in the numerator, we need to cancel out hours by having it in the denominator. Now let's do our unit analysis. The days cancel, and we're left with hours. Good. Hours cancel, we're left with minutes. Good. That's what we want. Your calculator will tell you that number. However, we need to consider sig figs. In 1.4 days, we've got 2 sig figs. Our equalities are definitions. 1 day equals 24 hours, 1 hour equals 60 minutes. That's set in stone. Those are exact. So we don't need to worry about those when it comes to sig figs. So our answer must have 2 sig figs. That 0 is our last retained digit. We're looking at the 1 to see if we round up or we just drop everything off. 1 is certainly 4 or less, so it's going to get dropped off. That would be 2,000. But this only has 1 sig fig. We need to represent this with 2 sig figs. Use scientific notation. That way you can show that you have a significant 0. And of course, don't forget units. If this still doesn't make sense to you, it's perfectly okay. It might still be fuzzy on the day that you have class. As long as it is less fuzzy at the end of class than it was at the beginning, we're making progress. Then when you start doing your homework, you may have more questions, which you can send to me using course messages, or you can come to office hours. Either way, we can get you the help you need. But hopefully, by the end of the lecture, the live lecture, you won't have as many question marks. So, why do we care about all of this unit conversion and using multiple unit, conversion factors and things like that? We really care about units for a lot of things. But one is toxicology. And one basic concept is that the dose is the difference between a poison and a cure. And you may have heard that kind of a number of different ways. It's definitely a quotable line. And one of the ways that we figure out what dose is poison and what dose is a cure is to evaluate the level of danger using laboratory animals, which is kind of sad. I'm sorry, animals. But science must go on, right? But we expose them to these substances and monitor their health, see what side effects they have, and then you see how many animals die depending on the dosage. And one measure of toxicity is the LD50. That's the lethal dose, where half of the test animals die if they're given that particular concentration or dose of the substance. Usually, you're measuring dosage in milligrams per kilogram of body mass or micrograms per kilogram of body mass. Now, I know everybody recognizes that cup of coffee. Coffee has caffeine. Caffeine is a stimulant. And let's be real about it. Caffeine is a drug. It affects how your body works. It can affect your thinking and your decision making. Caffeine has an LD50 of 192 milligrams per kilogram. Now, I don't remember how many cups of coffee that is. Not really something that you can drink. However, if you do energy drinks or anything like that that has really high levels of caffeine, you need to be careful. Those can be poison. Not trying to be your mom or anything, but, the more you know. So this table 2.8, has some of the LD50 values for substances tested in rats. So sugar, table sugar, really high LD50. I don't know that it would be possible to eat that much sugar in one sitting, but, I'm sure that maybe someone has tried. I hope not. But that's a lot of sugar. Boric acid, which you wouldn't want to eat anyway. Baking soda. We use it in, making things like pancakes and muffins and stuff like that. But you're certainly not using 4,200 milligrams. There's lots of different substances on here, some of which are controlled substances. Others are known poisons. So just be careful. The difference between a cure and poison is the dose. Okay. Now we're moving on to a different concept, density, but we're still going to be using the idea of conversion factors. This table has some common substances and their densities. So body fat, ice, muscle, all sorts of things. Density compares the mass of an object to its volume. And you may see any of 3 different ways that you can represent the units of density. grams per centimeter cubed, you'll see that for solids. Grams per milliliter, liquids. And for gases, it's grams per liter. Remember from the first part of the Chapter 2 lecture, 1 milliliter is the same thing as 1 centimeter cubed. Now, how do you figure out the density of a solid? You can't exactly figure out the volume necessarily in the same way that you could just say, oh, look at this cylinder, or look at this. We don't have shapes that are all nice and pretty and symmetrical that we can just do a simple calculation sometimes. Sometimes you have to measure the mass, or excuse me, the volume of an object by using volume displacement. What that means is you have a graduated cylinder that's got water in it or some other liquid, and you measure the volume initially. So let's say that your initial volume is 35.5 milliliters. Then you add your solid and you read the volume again. The difference between those two volumes is going to be the volume of your solid. Now the mass is pretty easy. The mass, you can just stick it on a scale, and there you go. You get the amount of grams, and you're good to go. This is just showing you the math. We talked about the concept, right? You have your initial amount of water, or whatever other liquid you're using. You put your solid in, the volume of the water increases, you read that volume. You take the difference between the two, right? So this was our final volume. This was our initial volume. The difference is 9.5 milliliters, which is the same thing as centimeters cubed. That 9.5 milliliters is the volume of water displaced, which is equal to the volume of your solid. Once you have that volume and you have your mass, then you can use the equation for density, which is just mass divided by volume. So let's do a learning check. What is the density in grams per centimeter cubed of a 48 gram sample if the level of water in a graduated cylinder rises from 25 ml to 33 ml after the metal is added? So we've got some numbers that we need to figure out where we're putting them. We're given the initial and final volume of the water. The initial volume is 25 milliliters. The final volume after the metal object is added is 33 milliliters. We also know that the mass is 48 grams. And to figure out density, we need our mass in grams divided by the volume, which is in centimeters cubed. Let's fill in some numbers. Before we can calculate the density, we've got to figure out that volume. And that's going to be the difference between the final volume and the initial volume. Remember the rules for adding and subtracting with sig figs. We've got to the tenths place on both of our measurements, so we need to represent this as 8.0, not just 8. We don't want to lose any significant figures. And 8 milliliters is the same thing as 8 centimeters cubed. Now we can take that value and put it into our density equation. We've got the mass, 48.0 grams, divided by 8.0 centimeters cubed. That's going to be 6, and that's what your calculator is going to say. But that doesn't have the right number of sig figs. 48.0 has 3 sig figs, and our volume 8.0 has 2 sig figs. We have to add a significant 0. Now we've got 2 sig figs in our answer. But this answer still isn't complete. The units, we've got grams being divided by centimeters cubed. Now we've got a complete answer. So just to recap, the first thing we did was identify what information we were given. I'm going to change colors here so you can see when I jot other things down. So we said our mass was given in the problem, and we were given levels of water, and within the context of the word problem, we could figure out 25 milliliters is the initial volume, and 33 milliliters was the final volume. The last piece of information we had to bring to the table was our knowledge of what density is, and it is the mass divided by volume. To figure out the volume, we used volume by displacement and just subtracted the initial from the final. That gave us 8 milliliters. We can rewrite that as 8 centimeters cubed. Then you take that volume, plunk it into your density equation, and there you go. If you have the volume and the density of a sample, then you can calculate the mass of the sample in grams if you use density as a conversion factor. Let's say that the density of a substance was 5.2 grams per centimeter cubed. I can write that 5.2 grams for every 1 centimeter cubed. This is a conversion factor. Let's do this sample problem to see what that really means. John took 2 teaspoons of cough syrup. If the syrup had a density of 1.20 grams per milliliter, and there's 5 milliliters in 1 teaspoon, what was the mass in grams of the cough syrup? We were given a lot of information here. We were given a density, of 1.20 grams per milliliter. We were given a volume of 2 teaspoons. And we were also given an equality. But it wasn't just, written blah equals blah. There is 5 milliliters in 1 teaspoon. That's an equality. This is a metric US equality, which means we're looking for one of them to be a measured number. That 5.0 milliliters is measured, which means that we need to consider sig figs. It's got 2 sig figs. I also want to write the 2 teaspoons correctly because we need to consider our sig figs from all sources. With all that information, what is our question? We need to know the number of grams in 2 teaspoons of this cough syrup. What else do we know? Well, we know that density is equal to mass divided by volume, and that we can rewrite the density as a conversion factor. Since we have an equality here, we can also write conversion factors for this equality. Looks like we have everything we need to set up an equation. Starting with these 2 teaspoons, we're going to go from teaspoons to milliliters. Then we're going to go from milliliters to grams. To go from teaspoons to milliliters, we're going to use this equality here. We need to have teaspoons in the denominator. Therefore, we're going to use this first one. To go from milliliters to grams, we use the density as a conversion factor. Now we need to check and make sure that our units cancel and we end up with the unit we actually want at the end. We cancel out our teaspoons because we have one in the numerator, one in the denominator, and we get to milliliters. We cancel out those milliliters and we're left with grams. That's exactly what we want. Now you can put it into your calculator. 2 times 5 divided by 1 multiplied by 1.2 divided by 1. Your calculator will tell you 24. Let's look back at all the sig figs we need to consider. We've got 2 sig figs in our measurement of the number of teaspoons that John took. We've got 2 sig figs in the measured value of milliliters in 1 teaspoon. And then we've got 3 sig figs in the density. That means that we need to have 2 sig figs here. So our calculator didn't do us any harm this time, but you still need to remember units. Without the units, your answer is incomplete, and an incomplete answer is wrong. Final concept. Specific gravity. It's the relationship between the density of a substance and the density of water. You divide the density of your sample by the density of water, which is 1 gram per mil at 4 degrees Celsius. And it doesn't have any units. So this is the one time where you can have a naked number and it's okay. A substance with a specific gravity of 1 means that it has the same density as the water, okay? Now let's say that you have a specific gravity equal to 5. Then that means that the density of your substance is 5 times the density of water. If your specific gravity is equal to, say, 0.5, your density of the substance is half the density of water. So that's just a little bit of an addition to the density concept. We can compare densities of substances using specific gravity, which is in itself a relationship between the density of a substance and the density of water. It doesn't have any units, so when you calculate a specific gravity, you should have just a number. This is the concept map for Chapter 2. I don't go through the concept map, but it is here for you if you like to see all of the different terms and things that we used and how they're related. Feel free to print this out, take notes, use it to study, and kind of have it in your mind how you need to connect all the different pieces that we went over. And this is, again, for the entire chapter. So all of the bits and pieces from the first part of the lecture, the chapter 2 part 1 lecture video, and this video are all present in the concept map. Thanks for watching. Make sure that if you somehow got through this video and didn't watch the first part, you go back and watch the first part. And always tune in to the live lecture for practice problems and details regarding assignments, exams, due dates, etc. Stay safe, and I'll see you in lecture.